When you build a robot prototype, your mind naturally goes to the hard physics. You worry about actuator torque, linkage kinematics, and gear ratios. These are tangible problems with clear formulas. But here is the uncomfortable truth. While engineers obsess over these visible mechanical challenges, they often underestimate the invisible integration layer where most of their time actually disappears. The real bottleneck isn't what your robot looks like, it's how its sensors talk to its brain in a chaotic world. Today we are unpacking why this invisible gap between simulation and reality consumes 80% of a prototype's lifecycle, turning months of work into endless debugging loops. The first major time sink lies in the latency introduced by sensor fusion pipelines. In your mind or on paper, you might imagine that when a camera sees an obstacle, the robot reacts instantly. But in physical hardware, perception and control are separated by complex data streams. Sub-millisecond timing mismatches between what a laser scanner detects and how quickly the motor controller can react create instability that is incredibly difficult to debug without high-fidelity timing traces. You spend days tuning PID loops only to realize your control frequency was fighting against sensor latency you didn't account for. This isn't just about speed, it's about synchronization. If your perception loop lags by a fraction of a second during a dynamic maneuver, the robot doesn't just make an error, it enters a state where its internal model no longer matches physical reality. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This brings us to the reality gap, which is often misunderstood as merely a simulation fidelity issue. In prototype building, this gap becomes a physical integration killer driven by environmental noise. Lab tests are conducted in controlled conditions with stable lighting and minimal vibration. But once you deploy outside, electromagnetic interference from motors creates electrical noise that corrupts sensor readings. Lighting variance alters how computer vision algorithms interpret depth. The data shows a 30 to 40% performance delta between these lab tests and field deployment. This isn't something you fix by tweaking a parameter in code. It forces engineers to rebuild the entire perception stack because the assumptions made during design were too idealized for the physical world they are trying to navigate. The third critical bottleneck is power distribution, often treated as an afterthought until failure occurs. In complex prototypes with multiple actuators and microcontrollers, voltage sags occur during actuator bursts when motors draw peak current. These dips cause brownouts in sensitive electronics that reset your microcontroller or glitch sensor data lines. The result looks exactly like a software bug to the untrained eye. Engineers spend weeks chasing phantom code errors only to discover their power supply cannot handle transient loads. This erratic behavior consumes disproportionate debugging time compared to mechanical design because it mimics logic failures while being purely electrical in nature. A robot that behaves erratically under load is often not an intelligence problem. It is a grounding and distribution failure masquerading as a control algorithm flaw. Beyond these physical constraints, the software integration layer presents its own systemic hurdles. Research into robot operating systems has revealed distinct software bugs within the framework itself, confirming that the invisible code layer is a critical bottleneck for many teams. These are not isolated incidents, but recurring issues where high entry barriers and complex framework synthesis create friction points. While graphical interfaces and plug-in architectures have improved accessibility, they cannot eliminate the fundamental complexity of stitching together disparate hardware drivers into a cohesive system. The failure rate in rapid prototyping often stems from poor tooling adoption rather than inherent physical impossibility, yet the time lost to troubleshooting these integration layers remains massive. The synthesis of these factors reveals that while mechanical design is the visible face of robotics, it is rarely the source of the deepest delays. When you focus solely on kinematics and actuators, you are building a machine in a vacuum. The true engineering challenge lies in making that machine survive the noise, latency, and power fluctuations of the real world. This requires shifting your mental model from designing for ideal conditions to designing for failure modes that only appear during deployment. If you can anticipate where these invisible layers will fail before they do, you stop treating integration as a post-design cleanup phase and start building it into the core architecture from day one. The path forward isn't about ignoring mechanics, it's about recognizing that mechanical success is meaningless without robust integration. By prioritizing timing analysis, environmental hardening, and power stability alongside your kinematic design, you can close the gap between what works in simulation and what survives on the floor. This shift from a physics-only mindset to an integrated systems approach is what separates prototypes that gather dust from machines that actually work. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.